Hello everyone, welcome to week 12 of the NPTEL course Material and Energy Balance. So this will be the last problem solving session and that will conclude the last topic for the course. This week we will start discussing and also practice some problems related to the topic of unsteady state material energy balances. So briefly about myself, I'm Chandra Paul and I'm a PhD scholar in the Department of Chemical Engineering at IIT Kanpur. And for the last 12 weeks, we have been meeting like this for on every Saturday. The recordings and the notes are made available to you. So let's start. When we think about unsteady state, it means that time is not constant here. So far, we have been doing the material energy balances under steady state conditions. Means with time, the properties are not changing, they are constant, which is why we consider the accumulation and depletion term in the overall material balance equation to be zero. But when we are saying unsteady state, that means time is a important variable here, and that has to be taken account of. So let's recall the material balance equation, the general material balance equation first. This is it. The accumulation and depletion within the system is equal to the transport into the system to the system boundary minus transport of material out of the system to the system boundary. Plus, if there is a reaction, then there will be generation of material within the system, or it is also possible that the material get consumed. So the generation and consumption terms comes under consideration when there is a chemical reaction. So this diagram here shows the same thing that is written here. If this rectangular box is the system with the system boundary, then here one side material is coming in, and here the surface, the defined surface, the surface area S1. And within the system, there is some generation and consumption going on, maybe a reaction. And over some period of time, the material is flowing out of the system boundary, and the defined area is S2. Okay. So let's try to put relevant terms here in this general equation to get a mathematical form of unsteady state material balance, and similarly for energy balance. So for a small time interval delta t, accumulation of mass of component A, let's say, is given by, so this material balance that I'm showing here is for component A. This is a component material balance. So for component A, accumulation term will be given by rho A, which is density of density of component A into the volume of the system at time t plus delta t minus rho A V at time t. Okay. So in the small interval delta t, this is the accumulation of or the mass. The dimension of this term is kg. If this rho A is defined as kg per meter cube, and the volume of the system is in meter cube. So it is the mass of component A that is accumulated within the system. Now mass flow is there, and there are two defined boundaries, S1 and S2, as I showed you previously. So the net, what is the net mass flow? Whatever mass is going inside through S1 minus mass coming out from the boundary or the surface area S2. So there, the terms will be again rho A density into velocity of the velocity at which the material is flowing, right? That is V. S is the surface area, and delta T is the time. Here also the net dimension, if you calculate, will come out to be kg or the mass. Now there are other surfaces other than the defined surface areas. Through there also material can flow across. So for considering that part, we are introducing another term W A dot into delta T. Here also the dimension is mass. And net generation or consumption term due to a chemical reaction is given by RA, which is the rate of the uh, reaction. Basically, that in other words defines the rate at which a component A is getting generated or consumed in the reaction into delta. So when we put all these terms in this particular expression, we get a form of 1. Similarly, we can write a total material balance equation. Means we are not considering one component at a time, a single component material balance, but overall. So here you can see only difference is that here reaction term is removed because net overall generation and consumption term, they will cancel each other out, right? Because you will do law of conservation of mass. So because of that, that term will be removed. Other than that, here the density will be the net density of all the materials. So we are not taking rho A, instead we are writing rho B, and rest all remains the same. Similarly, we can write energy balance here in this particular expression, since we are considering mass. If we consider accumulation of energy and transport of energy into the system, minus transport of energy out of the system, we consider that definition, then we can get energy balance expression given in 3. Here, this your left hand side term represents the net energy accumulation. This term, this represents the transport of transport of energy, transport of energy through the defined surfaces S1 and S2. This represents heat, and this term represents work. Lastly, this term represents the energy transport from the surfaces which are not defined, other surfaces. Okay? So now if we divide delta T term, right, on both sides of the equation in all the three equations, 1, 2, and 3, and take a limit of delta T tends to 0, then we will get differential equations like these. So equation 1, it becomes d rho AB by dt equals to minus delta rho BA Vs. So you can follow this, that this term became minus because we take final minus initial. So this term will come, this will come forward. Is why minus sign is there. So minus delta rho Vs plus V A dot plus R dot. Similarly, total material balance equation in differential form becomes this, and energy balance in differential form becomes this. Now we will start solving few problems that uses these uh, differential equations to solve unsteady state material balance or energy balance equations. This is the first question. Here you are told that there is a tank that holds 100 gallons of water salt solution. There is two component, water and salt. And in this tank, 4 pound of salt is dissolved. So this is, let's say, tank. It contains 100 gallon of water. And 4 pound is your salt. Water runs into the tank at the rate of 5 gallon per minute. 5 gallon of water goes into the tank, and it overflows at the same rate. So water comes out at the same rate. It is 5 gallon per minute. The mixing of the tank is adequate to keep the concentration of the salt uniform at all times. How much salt is in the tank at the end of 50 minutes? So they want to know the salt concentration or the salt mass is in LB after 50 minutes. Okay. Now assume that the density of salt solution is essentially the same as that of water. So water density is equals to water or the salt solution density. And this is the assumption. And here, when in the inlet, no salt is going in. All right. So for this particular process, let's assume, first of all, X as the pound of salt, the mass of salt at time t. So when initially at t is equals to 0, X is 4 pound. This is the initial condition. Now let's write your total energy balance term. So accumulation term will be M total, it's the mass in pound at T plus delta T time minus mass total pound at time T. It will be equals to inlet. So 5 gallon of water is going in per minute. Let's convert gallon to feet cube. 1 feet cube is 7.48 gallon. And your density of water is in pound per feet cube into delta T minute. Since I'm writing your total mass, right? Net mass, term for the net mass. I'll come to total balance in a minute. So this is in, and at the same rate, salt is salt solution also has some density, right? So okay, sorry. This is your total balance. This is your accumulation term. Is your inlet term in. The next term that I'm writing is outlet term. So in the outlet, what is going out is a salt solution at the same rate, that is 5 gallon per meter cube. Sorry, 5 gallon per minute. Let's convert gallon to feet cube. The density of the salt solution we have to take into delta T minute. Now, since the questions ask you to assume your density of water is same as density of salt, that means your net change in total mass during the time interval delta T it becomes 0. Okay. So we are not getting much information when we are doing total material balance. So let's do material balance for salt balance. So we know we considered X to be a variable that represents the mass of salt at time t. So let's write the accumulation term in that case as X is the mass of salt at time t plus delta t minus X is the mass of salt at time t. No salt is going in, so it will be in term will be 0. And what is coming out? 5 gallon of salt solution per minute is going out. And in this, we have to consider that X pound of salt is there, or X pound of salt is coming out per 100 gallon of water in time delta t minute. Okay. So what we get, if we write it as in this form, minus 0.05x. Let's divide both sides by delta t and take limit where delta t goes to 0. So what you get, you will get a differential equation, which is dx by dt is equals to minus 0.05x. So now we can convert it into this form, and from this form only we will be able to get the answer. That is, what is the salt concentration in the tank at the end of 50 minutes. If we solve this equation, this differential equation through integration, we'll be able to do it. But when we take integral, we have to do integration within limits. So what are those limits for integration? At t is equals to 0, you know X is 4 pound of salt is there. And at X is equals to 50 minute, at t is equals to 50 minutes, let's consider X is capital X. That is, you have to find. If you find the value of capital X, you will get the answer. So let's take definite limit here. For capital X, dx by x is 0, 50. This is the constant term, dt. So when you solve this, you should get ln capital X by 4 equals to minus 2.5, or ln 4 by x is equals to 2.5. So if you solve this, you should get x is so if we simplify this, you should get x by 4 by x is equals to e raised to the power 3.5. That is coming to be 12.2. And then x will be 4 by 12.2. It's just like simplification of it. So 4 by 12.2 is 0.328 pound of salt. the mass of salt that is left in the tank at the end of 15 minutes. Okay. Now let's do another question. So I'll give you a minute to have a read. So in this question, here also there is here we have to do material balance, unsolid material balance with no chemical reaction. The question states that there is a square tank, just 4 meters in on the side. Square tank. It's a square tank which is 4 meters on the side and 10 meters high, and water is filled to the brim with the water level. To find the time that is required to empty the tank through a hole in the bottom. So this is the hole. This is the small hole in the bottom whose surface area is 5 centimeters square, and water will come out. So we have to find the time T required to empty the tank. So what is known to us? We know at time t is equals to 0, height is 10 meter. Right? Height is h. Now here, first let's write the mass balance for water, which is leaving, it's coming out. Okay, it's coming out. Find the term for the mass of water. Mass of water leaving to 5 centimeters square hole. So 5 centimeters square is the area of the hole. We know 1 meter square is 10 raised to the power 4 centimeters square. Let's consider a variable term v star, which is the velocity. V star is the velocity of the water or average velocity of the water leaving the tank through this hole. V star is the average velocity of water leaving tank. Rho, let's consider rho as the density of water, kg per meter cube during the time delta t. So if we do are correct for the units, what we get a term whose dimension will be mass. It will come out to be 5 into 10 to the power minus 4 V star rho into delta T, right? So rho is the density of water. So this is the out term. In the mass balance equation, this is the out term. In term, the mass of water entering the water will be 0. What will be the accumulation or depletion term? So here we are going to write the depletion term. So depletion of water inside the tank will be expressed as so 4 meter is the here 4 meter is the side. So if we consider that instead of this hole, the bottom surface is completely open. So water will now come out from a square which is 4 by 4 or have a surface area of 16 centimeters square, right? So if the water has to come out of 16 centimeters square of hole with the density of rho, sorry, the unit is meter. And over the height of h m during time t plus delta t minus 16 meters square rho kg by meter cube to height m over time t. So when you remove the common terms, so another thing is at interval delta t, there will be change in the height of water by delta H. Okay, so that is why the final term will look like 16 rho H at t plus delta t minus H at t or 16 rho delta H unit is kg. This is your accumulation or depletion term in the um, mass balance equation for water. So when we put in the total mass balance, yes, there is only one component appropriate to write as mass balance or water balance. 16 rho delta H is the accumulation term equals in term in there is 0 minus out term is 5 into 10 to the power minus 4 star rho delta T. So if we divide this term with delta T on both sides, we get delta H by delta T equals 2 minus 5 into 10 to the power minus 4 V star root of is cancelled by 16 or TH by dt is equals to minus 5 into 10 to the power minus 4 V star by 16. Now, can we solve this? Or can we do an integration? Can. Because t is the independent variable, but there are two dependent variables, V star and H. So we have to find a term, to find the equation or relation between H and V star so that we can convert this equation in terms of only one dependent variable. So in order to do that, we have to uh, take help from the mechanical energy balance, which we already studied before. So this is the tank, let's say this is the water level. This is H1 height, this is H2 height. This is your axis. Let's say bottom there is 0. Here the water velocity is V1. The water is coming out from the bottom at the velocity V2. So we can simplify the mechanical energy balance equation like this, where kinetic energy, sorry, this term is for the kinetic energy, this term is for potential energy. What will be 0 here? Let's rewrite this equation in terms of V1 H1 and V2 H2. So V2 square minus V1 square by 2 plus G H2 minus H1 equals 0. Here V2 square, as I said, is the velocity of the water coming out from the bottom. V1 is the velocity of the water at the top. So we can apply a reasonable assumption that V1 is zero, close to zero. Okay. And here H2 is zero. So that simplifies stuff for us. V2 squared becomes minus 2G minus H1, or V2 is equals to root GH1. What is V2 here in terms of this expression that we wrote? V2 is basically V star, average velocity of water leaving the tank through this hole, right? That is V star. And because there is an aperture, so there will be some turbulence. So we have to add a correction term to account for that. So from fluid dynamics, that correction term is C, and has a value of 0.62. So V star is equals to 0.62 into 2GH. Here H1 is basically H, right? This is the final term that correlates V star and H. So now we can substitute V star here. We get dH by dt is equals to minus 5 raised to power minus 4 by 16. V star is 0.62 into root 2 H to the power half. We can simplify it further by basically um, combining the constant terms, and we get dH by H raised to the power half is equals to minus 1.08 raised to the power minus 4. Here minus term will not be there. Minus 1.08 raised to the power 4. Great. Do it myself. So 0.05 into 0.62 into root. Is divided by 16. So we get minus 2.74 raised to the power minus 5. Okay, this is the term that you get. Or You can also write it as, you can take this term here and do a reciprocal. So it will become minus 1.08 potential per 4 becomes dH by half. It's equals to dt. So we have to integrate it. So between the term limits at t is equals to 0, as I said, height was 10 meter, and at height h is equals to 0, how much time will it take? Let's consider a variable, unknown variable, theta. So if we, at here only we can do this 16 by 5 into 10 to the power minus 4.62. Eight, 7, each 16 by sorry, I'm just rechecking some of my calculations. So we haven't considered here the value of G, that is 9.8. We haven't considered that part. The 2 root of 9.8. Then it will become 16 by we are getting minus 1.2 2 times to the power 4. Minus 1.2 2 times to the power 4. So we have to basically find the value of theta, then our answer will be done. So let's integrate it. The constant values will come out. Here height will vary from t is equals to 0 plus 10. It becomes 0. pH, this will become at t is equals to 0. This will be theta dt. So we get minus 1.2 raised to power 4. So when you integrate this term, you should get 2 into root h in 0 to 10 equals to theta. Or theta is equals to, here because of the integration, this minus sign becomes plus. Or theta is equals to it becomes 7.6 into 10 to the power 4 seconds, or close to 80,000 seconds. Takes close to 80,000 seconds for entire water to come out from this tiny pore. Moving on. The next question. I'll give you guys a minute to quickly read it. So let's begin third problem. So the third problem states that there is a compound that dissolves in water at a rate proportional to the product of the amount undissolved and the difference between the concentration in saturated solution and the concentration in the actual solution at any time. This is an important statement that there is a compound that dissolves in water at a rate proportional to the product of the amount undissolved, and the difference between the concentration in saturated solution and the concentration in the actual solution at any time. The saturated solution of compound it contains 40 grams per 100 grams of water. When a test run that started with 20 kg of undissolved compound in 100 kg of pure compound is found that 5 kg is dissolved in 3 hours. If the test continues, then how many kilograms of the compound will remain undissolved at after 7 hours? Assume that the system is isothermal. Okay? So you have to only do material balance, no energy balance needed. So there is a solution, let's say a tank containing this solution. It is being stirred at all the times, the stirrer, and it contains the compound in undissolved state. So let's consider X to be a kg of undissolved compound at time t. At any time t, what we know, concentration of dissolved compound is if X is the amount of undissolved and you started with 20 kg, total is 20 kg in 100 grams of pure compound. So at any time t, concentration of dissolved compound would be 20 minus X by 100. This upper term represents kg of compound dissolved, kg dissolved compound. 20 kg is the total undissolved. Okay. At time t, X is the remaining is undissolved compound. So total undissolved minus X, it gives us or tells us how much is already dissolved by 100. It's the kg of pure wine. Okay. So pure is water, pure water. So what is the rate of dissolution? The first statement in the problem, it gives the uh, it gives us information about the rate of dissolution of compound. Rate of dissolution of compound given by rate in units kg per hour. It is proportional to amount of product undissolved. So X is the amount of product undissolved at any time t, and the difference between the concentration in the saturated solution. The saturated solution contains 40 grams per 100 grams of water. 40 grams, sorry, 40 grams. Since it's a ratio, we can change the units to 40 kg of compound by 100 kg water minus the concentration in the actual solution at any time. This is the actual solution concentration. It's 20 minus x by 100. Is also kg water, this kg compound. Now to remove this proportionality sign, we can add a proportionality constant k. So k into x into 40 by 100 is 20 minus x by 100. And this is your rate. And it's the rate of dissolution. Now we can use this particular term in the unsteady state material balance equation. Now, steady state material balance. The accumulation term is dx by dt. Nothing is going in, nothing is coming out. Here only dissolution of compound and some compound is becoming undissolved. So there is generation and consumption term is considered. So this rate that we found is basically generation minus consumption kind of. So we will replace this equation here. So it will become 4x well kx into 40 by 100 minus 20 minus x by 100. Or dx by dt becomes 100 comes out 40x minus 20x. It is 20 plus x. This is the term. You can further simplify it as dx by x into 20 plus x is equals to a by 100 into dt. So this equation can be split into two parts and then integrated. So we can write it as this. This comes from the knowledge of your plus 11. What are the conditions given to us for integration? At t is equals to 0, initially undissolved compound is 20 kg. Now they have tested one condition where they said 5 kg is dissolved in 3 hours. So at t is equals to 3 hours, the undissolved compound becomes 15. Now you have to find out what is the compound undissolved after 7 hours. So at t is equals to 7, we have to find x value, the value of x. First, we have to find the value of the proportionality constant k. So we can do that using these two conditions. So for finding K, let's integrate between x 20 is 15 dx by x minus 20 dx by x plus 20. A by 5 is constant. 6 0 is 3. Right? So what we get is ln x 20 and 2 minus is ln x plus 20 and 50 A by 5 into 3. So if you substitute the values of x and um, solve for ln, should get k is equals to minus 0.257. This term here on the left hand side is 0.15 into 3. is 0.25. So we are getting 0.25 is the value of p. Now we can substitute this value of p in this expression, and then find the value of x for time 700. So that we write that expression, dx, or we write this expression dx by x minus dx by a plus 20, x plus 20 is equals to q is minus 125 and 5. Now here integration will be given x limited, and let's consider a variable. Let's consider a variable here, capital X. Between times 0 to 7. Similarly, ln x minus ln x plus 20. This will come out to be minus 0.05 into 7. That is 0.35. Let's improvise this. Third improvisation. So when we try to find the values of these constants, one point zero four ln x by plus 20 x by x plus 20 amount 0.35, or x is equals to 0.35 x plus 20 x minus 0.35x. And 6. X is equals to 1.357. So X, that is the amount of undissolved compound after 7 hours, is finally 10.8 kg or 10.7. Is the amount of undissolved compound after 7 hours. So with this problem, I will end today's session. I hope these problem solving sessions will be useful to you, and I wish you all the best for your exams, those, at least for those of you who have registered for the certification exams. I um, request you guys to solve as many problems as possible with different topics of material energy balances that we have discussed so far. And yeah, all the best. Thank you for sharing.